Your phone can find you because Einstein was right. Imagine GPS with perfect satellites and perfect math, but no relativity. You tap Navigate, start driving, and the blue dot slowly slides off the road even though you are staying in your lane. By the end of the day, it can be wrong by about 10 kilometers. That is what happens if you pretend time is the same everywhere. GPS looks like a location system. Under the hood, it is a time system. Each satellite carries an atomic clock and broadcasts two things again and again. This is the time, and this is where I am. Your receiver listens to several satellites and measures how late each signal arrives. If you're wondering what an atomic clock is, I won't bore you with a definition. Just know it's a clock so accurate GPS can trust it. Now comes the neat trick. GPS turns late into far. Think of yelling in a canyon. You shout, then you hear the echo. The echo is late because sound needed time to travel. If you know the speed of sound, that lateness tells you how far the wall is. GPS does the same idea, but instead of sound, it uses a radio signal, and instead of a canyon wall, it uses a satellite. The only difference is the signal is absurdly fast, so the rule is simple. More late equals more far. Less late equals less far. That's it, just timing. Your phone takes the how late number and turns it into a distance. And here's why GPS is so strict about time. Light is so fast that even a tiny time mistake becomes a big distance mistake. Light travels about 30 centimeters in 1 nanosecond. A nanosecond is a billionth of a second. You don't feel a nanosecond. GPS does. For example, imagine you blink. Your blink takes maybe a tenth of a second. In that same time, light could circle Earth more than once. That's the scale we're dealing with. So when GPS says timing, it means timing so precise that a billionth of a second matters. Now your phone does this with multiple satellites at once. Each satellite gives your phone one, how far am I from you? Measurement. Here's the simplest way to picture what one measurement means. For example, pretend the satellite is a streetlight and you only know one fact. I'm exactly 100 meters from that streetlight. Where could you be? You could be in many places. You could walk all the way around it, staying 100 meters away, and every one of those spots would still fit. So one distance doesn't give one location. One distance gives many possible locations. Add a second satellite distance, and you must stand at a spot that satisfies both distances at the same time. The number of possible spots collapses. Add a third, and you narrow it down to one real location. Add a fourth, and your phone fixes the last missing piece, your phone's clock error. That's why GPS uses 4 satellites. It's not because 3 is weak, it's because your phone's clock is not an atomic clock. The 4th satellite lets your phone solve location and its own timing error together. Now we reach the Einstein part, because GPS only works if the satellite clocks stay synced with Earth time. And the satellite clocks do not naturally stay synced because satellites live in different conditions. They move fast, and they are higher up in Earth's gravity. Einstein's message here is practical. Speed changes how fast a clock ticks. Gravity changes how fast a clock ticks. This is not a one-time mismatch. It is a rate mismatch. If you ignore it, the error grows every second. First effect, speed. GPS satellites move around Earth at almost 4 kilometers per second. Special relativity says moving clocks tick a tiny bit slower compared to clocks on the ground. For example, imagine 2 identical timers. One stays on your desk, the other rides on a super fast ride all day. When you compare them, the moving one is behind by a tiny amount. For GPS, that slowdown works out to about 7 microseconds per day. Second effect, gravity. General relativity says, clocks deeper in gravity tick slower. Higher up, gravity is weaker, so clocks tick faster. For example, imagine gravity as a heavy blanket. Down on Earth, the blanket is thicker, so time runs a bit slower. Up at satellite height, the blanket is thinner, so time runs a bit faster. For GPS, that speed up is about 45 microseconds per day. Now, combining both stories, we get a speed effect and a gravity effect, and the gravity effect wins by numbers. So overall, the satellite clock runs about 38 microseconds per day faster than clocks on Earth. That sounds small until you convert it into GPS distance. At light speed, that turns into about 10 to 11 kilometers per day of position drift if you do nothing. Here's what that drift looks like. If a satellite clock runs fast, its timestamp is slightly ahead. Your phone thinks the signal left earlier, so it thinks the signal traveled longer. Longer travel time becomes farther. Farther changes the position solution. The blue dot slides even if you are not moving, so GPS must correct satellite time. Fix 1. Preset the satellite clock rate. Before launch, engineers set satellite clocks to tick a tiny bit slow on Earth. Once in orbit, relativity makes them run faster overall, and the two effects cancel to the correct rate. Fix 2. Keep updating the time. Real orbits are not perfect circles. Satellites change speed and altitude slightly, which changes the clock rate slightly. Ground stations track this and upload correction numbers. Satellites broadcast those numbers so receivers can correct the timestamp before turning late into far. Fix 3. Correct the math for Earth's rotation. Earth rotates while the signal is traveling from satellite to receiver, so the receiver's position has shifted slightly during the signal's flight. For example, throw a ball to a friend on a spinning merry-go-round. If you aim at where your friend is right now, you miss. You aim at where they will be when the ball arrives. GPS accounts for that same idea, but with light and Earth's rotation, so what looks like a simple blue dot is actually satellites broadcasting time and position, your phone measuring how late signals arrive, turning lateness into distance, combining multiple distances into one location, and correcting the satellite clocks because motion and gravity change the rate that time passes. That's why GPS needs Einstein.